So this is problem 3, and we're given a triangle, and we have to solve for x, y, and z. These two angles are 60 degrees. They add up to 120. If you see a situation like this, z has to be 60 because all three angles have to add up to 180. So z can only be 60 degrees. So z is 60, and now you know you've got an equilateral triangle, which means all three sides are equal in length. So x must equal 40, so we can put 40 in there, and 5y must also equal to 40, which means that y is equal to 8. So once you recognize that this is an equilateral triangle, the rest of that problem falls pretty quickly. Problem number 4 is a word problem. The angles of a triangle measure, and these are the three angles of a triangle, so let's draw ourselves a picture. One of the angles is 3x degrees, one of the angles is 2x plus 10 degrees, and one of the angles is 10x plus 20 degrees. And we have to classify the triangle by its angle measures and its side measures. So we've got to figure out what x is. If we solve for x, we can then solve for each of the angles. So how do we solve for x? Well, the biggest help here is the triangle sum theorem. The fact that the three angles added together equal 180 degrees. So let's go ahead and create an equation where we add the angles together and we set it equal to 180 degrees. We can solve this equation for x. Combining like terms gives us 15x plus 30 equals 180. And then by continuing to solve, we get 15x equals 150, x equals 10. So x is equal to 10. And now we can substitute back and see what the actual measures are of this triangle. So 3x is actually 30. 2x plus 10 is actually 30. And 10x plus 20 is 120. So these are the three angles of the triangle. It's an isosceles triangle. Two of the angles are equal. These are the base angles. So that makes it an isosceles triangle. And we're done. Let's move on to number 5. Now number 5 is a new kind of problem that we haven't encountered before yet in this unit. But as you might remember, we've looked at problems like this a few months ago. We've got an xy coordinate plane, and in the coordinate plane we have a triangle. And we're being asked to use coordinate geometry to prove that ABC is isosceles. Okay, so how do we prove that ABC is isosceles? Well, either by proving that two of the sides are congruent or that the base angles are congruent. Looking at this, which way do you think we are going to go? So if you guess that we're going to try to measure the two sides, you are correct. We can use the distance formula to measure two sides of this triangle. Actually, we don't know which two sides might be equal, so we're going to actually have to keep going and measure possibly all three sides until we find the two sides that have equal measure. So let's go ahead and let's do calculate the distance of AB, or the length of AB. And if you remember, what we can do here is, and you might have to kind of recall, there are two different ways to do this. One is by using the distance formula, and one is by drawing a right triangle and then using the Pythagorean theorem. So for AB, let's use the distance formula. Let's recall how to do that. We've got to get our coordinates for both A and B. And I'm going to try to use a different color pen so it will stand out a little bit from the black background. So let's go ahead and let's remember what are the coordinates of A. We've got negative 1, 2, 3, 4 on the x-axis. And then we've got positive 2 on the y. And then b is positive 2 on the x-axis. And then a positive 1, 2, 3, 4, 5 on the y-axis. Okay, so we've got to find the distance between point negative 4, 2 and 2, comma 5. So let's recall our distance formula. The distance formula is the square root of, and we've got to have y2 minus y1 squared plus x2 minus x1 squared, and the square root of the whole thing. And that is going to equal to the length of AB in this case. So remember, A is negative 4, 2. So let us call this our x1, y1. And let's call this our x2, y2. So then, labeling it like that, let's fill in for our distance formula. So y2 minus y1 is 5 minus 2 squared. Okay, and x2 minus x1 is 2 minus negative 4 squared. Okay, and let's remember that we've got to simplify this and then calculate it. So 5 minus 2 is 3. That gives us 3 squared. And here, 2 minus a negative 4 becomes a positive 4, which is 6 squared, which is 36. I'll put the 6 squared here, and then the next iteration, let's simplify. This is 9 plus 36, which is equal to the square root of 45. Okay, I could simplify this a little bit because 45 is 9 times 5. So it's the square root of 9 times the square root of 5, which is 3 times the square root of 5. Okay, so AB is 3 times the square root of 5. So far, so good. So we're going to have to find the length of at least one of the other sides. Let's go with BC. Okay, let's try to find the length of BC. And let's use the Pythagorean theorem this time. So remember that one way to do that is we're going to look at the coordinates of C, which is negative 1, comma, negative 1, 2, 3, 4. Negative 4. So negative 1 comma negative 4 is the coordinate of C. So one of the ways to locate where the vertex of the right triangle will be is either by sight, so we can go vertically down from B and then horizontally across from C and where they meet, or we can use the x value from one of the coordinates, like here 2, and use the y value from the other coordinate here, negative 4, so that we know we can go positive 2 and then 1, 2, 3, 4, negative 4. Either way, we will end up with our right triangle, which is like this, and we can now use the Pythagorean theorem to calculate BC. And to do that, we're going to count this side is a 1, 2, 3 in length side, so this is 3. And then this side here is a 1, 2, 3, 4, 5, 6, 7, 8, 9 in length, so that would be a 9 length side. So we're going to calculate the length of BC by using the Pythagorean theorem. So we know that BC squared is going to equal to 3 squared plus 9 squared. Okay, and that means BC squared is going to equal to 9 plus 81, which is equal to 90, or BC is equal to the square root of 90. Now we can simplify that, because that equals 3 times the square root of 10. And I'll let you figure out how that equals 3 times the square root of 10. Well, 3 times the square root of 5 and 3 times the square root of 10 are not equal, so we do not have yet any proof that this is an isosceles triangle. So it must be that the answer is going to lie with AC. We're going to have to calculate the length of AC and see if we can prove that through the length of AC. So let's go ahead and let's again use the Pythagorean theorem to write down the length of each of the sides. So first we've got to calculate where our vertex of the right triangle will be. This time I'll just do it by looking downward from A and leftward from C, and where they meet will be the vertex. So now I'm going to put on a vertical side and a horizontal side, and now let's again count the length of this side. This would be 1, 2, 3 in length. This side is 1, 2, 3, 4, 5, 6 in length. So our length of AC, and I'll go to the top of this to do the calculations, again to use the Pythagorean theorem, AC squared, which is the hypotenuse squared, is equal to 3 squared plus 6 squared. So let's go ahead. 3 squared plus 6 squared is equal to 9 plus 36. AC squared is equal to 45, or AC is equal to the square root of 45, which is the same thing as 3 times the square root of 5. So what we found is that AC is equal to 3 times the square root of 5, AB is equal to 3 times the square root of 5, and we can prove using a combination of the distance formula and the Pythagorean theorem that ABC is an isosceles triangle, and the lengths of the sides that have the equal length are AB and AC.